right, strong acids are very similar to soluble compounds. We've been talking a lot about solubility in Chapter 4. And the definition of a strong acid is that it completely dissociates or breaks apart into ions. So sample problem 4.12 deals with this. It says, how many H plus ions are in 25.3 milliliters of 1.4 molar nitric acid? So the first step here is to write down what we know. I know I have 25.3 milliliters of nitric acid. Now I need to know the formula of nitric acid. And so that's HNO3. And that's something maybe you just have to memorize. If you look on page 159, table 4.2, it has some strong and weak acids listed there. And so that's how I knew the formula for nitric acid. It's just HNO3. So anyways, and I need to convert that to moles, right? And how did I know I needed to convert that to moles? Let's talk about that. This says how many H plus ions are in 25 milliliters of nitric acid. Now this is talking about the number of something, right? How many ions, or the number of entities. And remember Avogadro's number. It's 6.022 times 10 to the 23 entities per 1 mole. Right, so that's how I knew I was going to need to convert these milliliters to moles. Right, they're telling me the amount of this nitric acid I have in milliliters, and they're wanting to know how many ions, and I know Avogadro's number is definitely a conversion factor that'll tell me the number of ions, right, or entities. But I got to first get things into moles. So let's see, the concentration they've given me here, 1.4 molar nitric acid. That's the same thing as 1.4 moles per liter, right? Because molar concentrations are in moles per liter. So I have milliliters, so I'm first going to convert that to liters. And I know that there's 1,000 milliliters in 1 liter. And now, from the molar concentration, for every 1 liter, there's 1.4 moles of nitric acid, right? HNO3. So let me check my units. I've got milliliters divided by milliliters, liters divided by liters. I'm going to be left in moles. That's good. That's what we're looking for here. Let me get some room. See, equals. So I'm going to have 25.3 times 1.4 divided by 1,000. And that's going to be 0.03542 moles of HNO3. And now I can go from moles of nitric acid to moles of hydrogen. And why am I doing that? Why am I going to do that? Because they're interested in hydrogen, right? Just the H plus ions. So let me rewrite down what we just figured out. 0.03542 moles of HNO3. And I've got to ask myself, what conversion factor can get me from moles of nitric acid to just moles of hydrogen? There it is, right? I mean, the molecular formula. It tells me for every 1 mole of HNO3, I have 1 hydrogen there, right? That's what the formula tells me. So 1 mole HNO3, I got 1 mole of H plus. So that means I'm going to have 0.03542 moles of H plus. And Avogadro's number will tell me that in 1 mole, there's 6.022 times 10 to the 23 of anything, and I'm talking about H plus ions, so that's what I'm going to put in the top. Moles divided by moles cancel. So let's see what we have. So 0.03542 times 6.022 times 10 raised to the 23 equals, and I got 2.13 times 10 to the 22 hydrogen ions. And so that's how many ions would be in that 25.3 milliliters. That's how many H plus ions. That's a big number, right? And that's fine because Avogadro's number is a big number. So we should have a lot of those hydrogens floating around in that solution.